Good afternoon. I will talk about a reference model for airborne wind energy systems, a case study. I'm Uwe Fechner. I have a PhD from Delft University of Technology here in Holland on the design of kite power control systems. I'm a member of the International Energy Agency work group on airborne wind energy and postdoc at Delft University of Technology on physics-informed learning control of wind energy systems. I'm using Julia also, like the last speaker, since version 0.3, which is about 10 years ago. I want to give an overview over my presentation. First, I will explain the concept of airborne wind energy. Not all of you will know it. The status of the industry, and what are airborne wind energy systems models used for, and why are they important. Then I will explain the reference model that we are developing. It consists of about 10 Julia packages. Most important are kite simulators, kite controllers, and kite models. Then I will show the 3D app that we developed, the physics on which this is based, which is a particle system model, and then go a little bit more in detail how it was to develop this large piece of software using Julia, which challenges I faced, what the performance looks like, and talk about my experience developing such a large Julia project. Finally, I give an outlook. So how does airborne wind energy work? Who knows it? Who knows how airborne wind energy works? One, two people at least. That's something. So I should explain it. So there are different concepts. I explain here only one of the concepts. My model assumes that you have a wing that is attached via a tether to a ground station. So the wing flies figures of 8 like these kite servers at the beach. It pulls hard on the tether. The tether is on a drum which is attached to a generator on the ground, and in this way generates electricity. When it reached the maximum height, which might be something like 300 meters, then we change the angle of attack and reel it back in at a low lift and a low force. So 80% of the time we reel out, 20% we reel in. So that's a pump, we call it pumping mode of operation. Status of the airborne wind energy industry. So I show here two examples. On the left-hand side, you see SkySails, which is a German company. They have two systems in operation. One of them in northern Germany, near my hometown, and one on Mauritius. And they have a lot of people try to buy their system. They also have a certified power curve, so it was certified by an independent party how much power they can harvest. And then Enerkite is another German company from Berlin, from Brandenburg. And they have a rigid wing kite, and they use rotational launch and landing. That means they fly like this with a kite on the arm, and if they go fast enough, then it just goes out and goes into the air, and that's the way they launch and land. And so they can launch and land also if there's zero wind. Launching with zero wind doesn't make much sense, but landing might be required. So they also have a 100 kilowatt system. Yeah, so that's the state of the art. For the future, we want to go to bigger systems. This is just one example from Switzerland. They made a very nice concept study of a 1 megawatt system, which you can deploy in 4 containers. So it's very mobile. They have very strong interest, for example, from the mining industry. They cannot put a wind turbine next to their mine if their mine is there only for 4 years, and then they move further. But such a system you could put there, and you can put it in a container just 3 days and then move to a new location. To develop these large rigid wings, it's very expensive and time consuming. We had one company in The Hague that tried that and failed. But yeah, there are the companies who pick up and hopefully have a better plan. So, for example, here, these guys, they want to go first to 20 kilowatt, then to 100, then to 1 megawatt. So they already have a 20 kilowatt system, but this upscaling, it takes time. So why do we need airborne wind energy system models? Yeah, well, I work at the university, so I like teaching, so for educational purposes, of course, to explain people how airborne wind energy works, and that students can learn the impact of changing parameters. But then we need controllers, so it's not easy to develop such a controller. We want to have optimal control. We want to have trajectory optimization. We want to be able to test what happens if you have strange wind profiles. Sometimes the wind at 100 meters is very strong, at 300 meters very weak. Depending on the time of day, this is always changing. And the controller must, of course, work in any wind conditions. For the wing design, we need models to determine the loads and the impact of changes to the wing. The ground station design, and for the wind resource assessment. Yeah, to build such models, I developed JuliaCon power tools. I'm working on this now 2.5 years, but I worked on the same topic before, but using Python and C++, but now I use Julia. I'm much more happy. It works much better, much more fun. Also much more maintainable, which is also important. I have this large number of packages. Yeah, everything starts with the kite utils. There are the settings files. So I read them from a YAML file, put them in a struct. Then we have kite pod models. The kite pod hangs below the kite, and it's a kind of mini robot that pulls on the lines and steers the kite. Then the winch model at the ground, atmospheric models, kite viewers, so that is this 3D viewer, I will show it in a minute, kite controllers, which includes flight path planning, and kite simulators is a meta package that pulls in everything else. So this is the kite app. I'm pretty happy about it. It has this input for YAML files per project. You can change the project using a GUI. Output is a log file in arrow format. Arrow formats is very nice if you have large log files and want to be able to read and write them fast. Of course, you can convert them to CSV or data frame. It's a 3D simulation that works up to 12 times real time, which is way faster than any other simulator that is out there. Most simulators work at 10% real time or whatever. They are written in Simulink or in Python. And we can create 2D plots and have a statistics window. I want to shortly show you this software in action. And so it's based on Marquis. And I'm very happy about Marquis. It's a very powerful 3D GUI system. And I am running now the simulation in 12 times real time. You can see how the kite flies figures of 8. The tether is reeling out. You can see here the power. Now it's negative because we are reeling in. The harvested energy, the tether force, and everything else. On the top right, you see depower and steering. Depower means a change of angle of attack. And yeah, we can zoom in, reset this. And then if we have this, we can plot, lots of different plots. Here you see the height, the elevation angle, the azimuth angle. You can also see the power that is generated. You see the energy that is harvested, it goes up, and if you reel in, it goes down a little bit. This is already pretty nice, and I like this plot. You can see is the trajectory as it is intended to be, and you also get in the end statistics, because that's what you are interested in the end, how much power comes out of the system, how much energy was harvested. But you are also interested in the question, are the constraints kept by the controller? We don't want to fly too low, also not too high. So this is a nice GUI program. I continue with the presentation. Yeah, that's the azimuth elevation plot. So what is the simulation based on? It's based on a particle system model. That means I have for the tether, let's say 6 particles, can also be 12. For the kite, 4 particles. These are all point masses. They are connected with spring damper elements. And a little bit tricky is how do you implement the reel out and the reel in. And I do this by changing the unstretched length of the springs. And aerodynamic forces are attached to the points C, D, and B. So it's a kind of 3-plate model with pre-calculated lift and drag curves. And it works very well. So what were challenges? Well, the first challenge was to find initial conditions that are close enough for the solver not to fail. This is mainly due to the high stiffness of the system. A root finding algorithm is used, and I do a 2-step approach. First, I run the solver with a lower stiffness than it has in reality, and then I switch it to the full stiffness, and that works pretty well. Then the default norm function, at some point it became slower. I was annoyed. I made my system so nice and fast. Then it becomes slow, so I replaced it with my own norm functions. At some point, the EDA solver stopped to work with M vectors. That was also interesting. I mean, it's this, it worked, but it was not part of the API. And I didn't know that was not officially supported. It was just worked by accident. So this required some code changes to make it work again. Luckily, this is no longer an issue with the new GMRES solver. So I'm very happy with this new solver implemented in Julia by a master student from Switzerland, a Chinese master student. It's so much better than anything else. Much faster, much more accurate, and much lower memory allocations. If we look at the performance compared to Python plus Numba, we have 10 times the basic performance. So I have a residual function. I call it with the vector of the position and the velocity of the particles, and I get back a residual which should be 0. And this function now needs about 1 microsecond. With Python it was 10 microseconds. But in addition, this new solver also gives another 10 times advantage. So we have together 100 times advantage if we work single-threaded. And in Julia, you can also use multi-threading. If you are optimizing your controller, try different parameters, you can do that in parallel. So with one thread, I have already 66 times real time, which is very nice if you need to optimize or if you try machine learning. But I also implement real-time simulations. That is important if you want to test the real controllers, the real flight controllers, which is happening. We have a startup in Delft that builds these systems, and they are starting to use my software, and they need to test their controllers in real time. You see here, this is kind of soft real time. There's no hard guarantee that it is met, but you can see, yeah, there are peaks of 7 milliseconds per iteration, and that time that we have without losing frames is 8 or 2 milliseconds. So even with 6 times faster than real time, it works. Yeah. So important is that you log what is happening. Important is try to avoid memory allocations, turn off garbage collection. I'm happy if I can run the simulation for 1,000 seconds, and if I have 32 gigabyte RAM, it doesn't run out of memory. So I just turn off the garbage collector. I use Linux, that helps a lot. And then measure and optimize the execution time of each part of your program. Still missing is a solver for fully implicit DAE systems that does not allocate. The current solver has an interface that should make this possible, but it is buggy and doesn't do what it's supposed to do. So there's still room for improvement. On the left-hand side, you see an example how to do real-time simulations. So in the beginning, I store the start time in nanoseconds. Then I calculate the control input, steering and depower. Then I call the step function of the solver. And then I update the GUI. And then I have this wait until function, which is part of the timers.gl package. And then I say I want to wait until the start time plus delta t. Always sleep true means I always sleep that is needed to update the GUI. And then I update the start time and then loop again. And this allows a very accurate real-time performance. So about my experiences. I was happy about the code. It's very clean and maintainable. The aerodynamic model would fit on one screen. It's 30 lines of code or maybe 40. The performance is outstanding. The NICE has a very good performance. Thanks again a lot for the developers of Mackie for their support. Installing of the resulting code is easy, but requires a significant amount of compilation time. So I always build a custom system image. It's not really required, but if you do it, then the startup time is maybe 4 seconds. If you don't do it, it's significantly longer. Now the bad. Developing code that consists of a set of packages can be slow down the development. It is challenging to work on different packages in parallel. So I have not only package A that comes on package B, but A that depends on B, which depends on C. And then if I have to change C, often I, in the end, have to make a new release because it really propagates. And that then in the end might take a few days. I know there are ways to get around it, but often I just make a new release. Creating unified documentation is challenging. The good thing is the new version of Documenter can cross-link between different packages, and I want to do that when I find the time. Here, the custom system image. I mean, what I do in all not in all, but in all bigger packages, like kite models or kite controllers, I have a script create system image. It creates a system image for all and includes all packages that the package I'm developing depends on. So I can use revise to work on the current package, but all the dependencies are in the system image, so I can quickly restart Julia if required. Then the last point, the stability of the ecosystem is not that good. A couple of times per year it is needed to make code changes to adapt to changes to key packages. This is a bit unfortunate. It shouldn't be like that. There should not be breaking changes in minor package versions, but it happens. Yeah, and I use something like 40 packages, and that one of them has a breaking change unintentionally. Yeah, it happens. But it's also not a big deal in the moment. But it would be nice if I'm really looking forward to the point in time when marquee.gl reaches version 1.0 and has a stable API. So that would be very nice. Outlook, next steps. I want to adapt automatically to changing wind speeds, add wind turbulence and wind gusts. I did that in Python, not yet converted to Julia. Add a Python interface, which is mostly done, so Python call worked nicely. Implement learning control that learns optimal controller parameters after changes to the model or the environment. That is really the main task for me for this year. And that is, if we say we have a reference model for the international community, that is important because in a company, an investor, a government, they want to use this simulator then for their wind conditions, their system, and then it must tune the parameters automatically and spit out a power curve. And add a rigid wing model. I hope I find a master student in Italy who does that. Yeah, so these are the packages I developed. If you look at the helper packages, time_GL will be interesting for anybody of you who wants to do real-time. Joysticks for anybody of you who wants to use a joystick. PKG helpers helps me to freeze packages in the TOML file, package TOML file. And control plots is my own control plotting library, and I like it, but it's, yeah. The main page, and if you want to install it, it's easy. Yeah? But if you use Linux, try to install matplotlib first. Not really required, but works better. And maybe what is different from other people who deploy an application is I deploy the application as package, but then I call the function here init project, which copies a certain folder structure like an input data folder, an output data folder, and an examples folder. It copies all that to your project folder. So, and I also have this script create system image. And if you executed that, then you have your system image. And then I have a script run Julia that starts Julia with the correct parameters and loads the system image. And then you can just try out the examples. Yeah, so if you have some time and are interested in a moment, try it out. And that's it. Thank you very much.
Yep.
Thank you very much for your nice presentation. You mentioned an issue with GMRS and M vectors, and it was in part already resolved. Could you please explain again what the issue is and what the status now is with GMRS?
Issue with GMRS. First of all, it works very well, much better than either. The issue is that it allocates. In theory, there is an interface where you provide a static vector for the state that shall be solved, and it should happen in place. So that means it should not allocate, because it just works on the vector that you provide. But that doesn't work. It does allocate. And I did not find out yet where.
But I do imagine that GMRS need to allocate its search space internally.
It allocates even though it shouldn't. And first, I've also found one issue that was an option to log certain parameters. I turned this logging off, so it allocates a lot less, but it still allocates, but it shouldn't. And that, I think that could be fixed. It just needs someone who invests some time.
Thank you.
Thank you for your presentation. I was wondering if your simulation includes some type of control, and if it's needed for this type of systems to perform some optimal control, and if yes, is it possible regarding the real-time constraints?
Yeah, yes. It includes the package kite controllers, which is pretty huge, and actually the result of my PhD in the end. The algorithms are the results of my PhD. What I did actually when I developed that control, I developed it in Simulink and then translated it to Python and then to Julia. It works, and it's fast and it's simple. It's mainly PID control with nonlinear dynamic inversion. So it doesn't use any advanced controllers. There is another simulation package for these type of airborne wind energy systems that uses optimal control. Yeah, I still want to look into it, but I did not find the time yet. Yes, you need controllers, and there are many papers about it, how you can do it, and many different approaches.
Thank you.
Thank you. Could you please tell a bit more about this lifting line methodology that you just mentioning in the end?
Not really, because I'm electrical engineer, not an aerodynamic engineer. I have one colleague who is a PhD researcher in Delft who developed a very nice kite model in the context already of his master thesis. And I will convert his model and integrate it with my code later this year. Yeah. But if you want to Google it, you can Google Roland Schmel Delft or also my name, or send me an email and I can forward.
Have you verified this against real life data?
Yes. So the first paper, which is given as reference on the second slide, there we validated it against measurement data. The problem is with this validation that I did, that we did not have a LiDAR to measure the wind speed at the height of the kite. So I had to estimate the wind speed at the same time as the kite parameters, which is a bit debatable. But we did a test campaign 2 years ago, and yeah, with LiDAR measurements, but again with a different kite. Yeah, I plan to validate the model, or we will have a better kite model and a better validation end of the year.